So in this example, we're given the H field and we need to find the E field. So the H field is equal to 0.02 y hat amperes per meter, and then K vector is equal to 3x hat minus 4z hat, and then we need to find the electric field, E field, and then our medium is in vacuum, and at t equals 0 origin. So first thing, we're going to write out our H field. So we know that the direction is in the y hat direction. Our magnitude is 0.02. And then since at t equals 0, cosine survives, it's 1. So we write cosine as our phase, omega t minus 3x plus 4z amperes per meter. So I'm going to explain why we write this as negative 3x plus 4z. So an example is, say we have a line y equals x plus 2. This line is actually shifting to the left by 2 units. And though it's shifting to the left by 2 units, we write it as positive 2. And that's what we're saying here is, like, if it's negative 3x, we're really meaning positive 3x, and if it's 4z, we're meaning negative z. And then the next thing is describing why we don't have hats on that portion, and that's because k, which is the wave number, is equal to 2 pi over lambda. Lambda is a wavelength, so it's scalar. So it has magnitude, but no direction, so there's no hats on these. And k, which is the wave number, is what we describe here. And then we need to find omega, and omega is the angular frequency, and that is equal to ck, which is c is the speed of light, and k is the wave number, which is the magnitude of k. In our case, it would be 3 squared plus 4 squared. The square root of that would just be 5. And so we get our omega to equal 1.5 times 10 to the 9th radians per second. And now we are going to find the direction of our E field. So we're going to label our axis Z and X, and then Y will be going into the board. So drawing the direction of our K, it would be 3x hat minus 4z, so it would be in this quadrant, and then H would be going into the board, which is our positive y direction. And then to get the direction of E, we are going to use our right-hand rule. So E hat cross H hat is equal to K hat. Using this rule, we'll find that the direction of E will be in the lower left quadrant. And so we need to write E as a unit vector. Since K is a 3 to 4 ratio, E will be a 4 to 3 ratio. And then we divide by, when we write the direction for E, we would divide by the magnitude, because it's not a unit vector. So then writing out our E field, we'll get negative 4x hat minus 3z hat over 5. We're dividing by the magnitude, again, because it's not a unit vector. And then cosine, our phase will be the same as our H field because it's true as long as the medium of the wave is propagating is in lossless, which is in our case. So therefore, the information that we have for the phase of H will be the same for E. And then E field, so it will be volts. The units will be volts per meter. And now we want to find the magnitude. So the magnitude is equal to E naught over H naught, which is equal to eta naught. Eta naught is the wave impedance. And since the medium is in vacuum, we know that the wave impedance is just equal to 377 ohms. So our H naught is 0.02, and our eta naught is going to be 377. So E naught would be equal to 7.54 as our magnitude of the E field. So we're going to write this here. And that's it. That's our answer for the for our electric field given the H field.